Today, we're going to break down one of the most fundamental and honestly most challenging concepts in building massive systems: partitioning. This is the secret sauce that lets the world's biggest databases handle data that simply can't fit on one machine. The real question isn't if you'll need to do this, it's when, and more importantly, how you'll do it without breaking everything.
Let's just start with a brutal truth every single engineer eventually faces: the single node wall, right? You build something amazing, people love it, and then all of a sudden your database machine is just screaming for help. You can throw more money at it, make it bigger, faster, but you will always hit a hard limit. And that ceiling, that's where most systems die.
So when your data gets too big for one machine, you really have two choices. You could give every machine a full copy, that's called replication, and it's great for handling more reads and surviving failures, or you can give every machine its own unique slice of the data, and that is partitioning, and that's exactly what we're diving into today.
Okay, so the big question is, how do we actually slice up that data? It sounds simple, but the strategy you pick has these massive downstream consequences for your system's performance. And really, there are two main schools of thought.
First up, we've got key range partitioning. And honestly, the best analogy for this is something you probably haven't seen in a while: a classic multi-volume paper encyclopedia.
Think about it. If you want to find information about zebras, you don't search every single volume, do you? No, you go straight to the TZ volume. In exactly the same way, the database knows precisely which partition to look in based on the key. This makes queries for a range of keys, say all sales from March 1st to March 15th, incredibly fast and super efficient.
But this strategy has a huge vulnerability. What if your keys are sequential, like timestamps from user events? Well, all of your new data, everything that's happening right now, is going to have keys that fall into that same final partition. And that means all your write traffic is just hammering a single machine, creating this huge bottleneck, while all your other partitions are just sitting there, totally bored and idle.
So to solve that hotspot problem, we have our second core strategy: hash partitioning. The analogy here is perfect. Instead of neatly organizing our data, we're going to do the complete opposite. We're going to shuffle it, just like a deck of cards before a game.
By running each key through a consistent hash function, even perfectly sequential keys, like our timestamps, get scattered almost randomly across all the available partitions. It is a brilliant way to evenly distribute write-heavy workloads and make sure no single node gets all the aces, or, in our case, all the hot data.
And this brings us to the crucial point, this fundamental trade-off. With key range, you get those super efficient range scans, but you're always living with that risk of hotspots. With hash partitioning, you get that beautiful, even load distribution, but the same range scans become incredibly expensive, forcing the database to go ask every single node for its data.
But even a perfectly even data distribution can't save you from some really tricky real-world problems. The theory is always clean, right? But reality? Reality is messy.
So what happens when millions of people try to write to the exact same key at the exact same time? Just imagine a celebrity posts something, and millions of followers all comment or like it instantly.
Well, hashing that post's ID is always going to produce the same result, which means all of that activity floods a single partition. This is a case where our perfect hash partitioning strategy just completely fails us. And the solution can't come from the database, it has to be at the application level. For instance, you could add a random suffix to the key, like post ID_1, post ID_2, and so on, to artificially spread the writes out. The trade-off, of course, is that now to read all the comments, your application has to be smart enough to go looking for all those different keys.
Now, so far, we've only talked about finding data by its primary key. But what about querying on something else, like finding all users in a specific city, or all cars that happen to be red? This is where secondary indexes come in, and boy, do they create a huge challenge for partition systems.
So the most common approach is what's called a local index. It's pretty simple. Each partition just maintains its own separate index, but only for the data it holds. This means when you write a new document, the entire operation, writing the data and updating the index, all happens on one machine. And that makes writes very, very fast and nicely self-contained. But here's the catch. To find all the red cars in your database, you now have to ask every single partition if it has any red cars. This is called scatter/gather. And this is a perfect illustration of a really dangerous concept called tail latency amplification, because your query is only as fast as your slowest responding node.
Just one slow machine can hold up the entire response for everyone. The alternative to that is a global index. You could think of this as a completely separate database whose only job is to be an index. Now, this index is itself partitioned. So a query for red cars goes to one specific partition of the index, which then acts like a map, telling you exactly which data partitions contain the information you actually need.
So reads are now incredibly fast and targeted, completely avoiding that whole scatter/gather mess. But the trade-off is massive. Writes become slow and really complex. A single new document might require updating multiple index partitions spread all across the cluster. And this often means the index updates happen asynchronously, leading to eventual consistency, where a read might not see the very latest write. A cluster is never static, right? You're adding machines, machines fail, data grows. So how do we add or remove nodes without any downtime? And how do clients even know where to find their data when things are constantly moving around?
First, a critical rule. Please never use the modulo n strategy for partitioning, where n is just your number of nodes. It seems so simple and elegant, but adding just one machine forces this catastrophic reshuffling of nearly all your data across the entire cluster. It is a true operational nightmare.
Instead, production systems use much smarter strategies to minimize all that data movement. The most common one is to create a fixed number of partitions right up front, way more than you have nodes, and then you just reassign a few of those logical partitions to a new machine when you add one. Other systems will dynamically split partitions when they get too big, or, like Cassandra, they use these clever algorithms to tie the number of partitions to the number of nodes in the cluster.
Okay, so with partitions constantly moving around, how does your application know which node actually holds the data it needs? This is a classic service discovery problem.
The solution, very often, is a coordination service, like Apache Zookeeper, which acts as the master librarian for the entire cluster. It holds the single source of truth, the authoritative map of which partition lives on which physical node. So when a partition moves during rebalancing, Zookeeper notifies everyone subscribed to that information, whether that's a dedicated routing service or the clients themselves, so they always know exactly which shelf holds the book they're looking for.
All right, so what's really interesting is how all these complex trade-offs come together in the real world. So let's look at two key decision matrices that basically summarize everything we've just talked about.
First up, choosing your primary partitioning strategy. As you can see, the choice is totally driven by your query patterns. If you're doing a lot of range queries, like fetching all sensor data from the last hour, key range is your best friend. It's incredibly efficient. But if your main goal is to handle a massive volume of individual writes, like on a high-traffic OLTP system, then hash partitioning is the way to go, because it guarantees that load will be spread evenly.
And now for secondary indexes, where it's an equally clear, but let's be honest, painful trade-off between read and write performance. Is your workload write-heavy? Local indexes are your best bet. They'll keep that write latency low. But if your system is read-heavy and you absolutely cannot tolerate slow scatter/gather queries, well, then you'll need to pay the price of a global index. That gives you blazing fast reads, but at the cost of slower, more complex writes. You really have to analyze your workload and choose your pain. So if there's one thing you take away from this, let it be this. Partitioning is not just a feature you turn on. It is a foundational architectural choice. Every single decision, how you design your keys, your indexing strategy, your rebalancing policy, it all cascades directly into how your system behaves at scale. It dictates your performance, your complexity, and ultimately, whether your on-call engineer can get any sleep when things inevitably go wrong.